So you have a sample that contains iron and oxygen. Then you're given the masses of iron and oxygen in the sample. We're going to use that to determine the empirical formula of the sample. In other words, the chemical formula based on the experimental information given. So this works very similar to previous problem. The difference on this one is you're actually given the mass. There's no need to come up with a sample size. So let's walk through and get the moles of each, and then go from there. So there's the mass of iron. We'll use the molar mass to figure out how many moles are actually in the sample. And that's for iron. We'll do the same thing for oxygen. Again, using the molar mass from the periodic table. And let's look and see what we have so far. Now, up to this point, this is no different than the previous problem we did. Remember that it's the relative number of moles. Water, H2O, has a ratio of 2 moles of hydrogen to 1 mole of oxygen, regardless of sample size. So in this one, we only have 2 elements, iron and oxygen, which makes it a little easier. And which one do we pick to do our ratio? You pick the smaller one. So we'll divide oxygen by iron. And that comes out to be 1.334. So our information says that for every mole of iron, we have 1.334 moles of oxygen. And, whoa, hang on. Now, before we had ratios that were very close to whole numbers, and so we just rounded it to the nearest whole number. That's not close. That you can't round. We need to figure out mathematically what to do with this one to get a ratio of small whole numbers. All right, so look down below. This is where we are. The ratio is 1.334 to 1. Maybe if I put that in fraction form, you'll be able to see it better. So that's 1 1/3, which is 4/3. Now I want a whole number. So what can I multiply 4/3 by to get a whole number? 3. But see, this seems to be suggesting that, our mole ratio is 4 moles of oxygen to 1 mole of iron, and that's not correct. I have to preserve the 1.334 to 1. So remember, mathematically, whatever you do to one part, you do the same thing to the other part. So since we multiplied the oxygen ratio by 3, we have to multiply the iron ratio, which I know is iron to itself, but also by 3. So this means the mole ratio of oxygen to iron is 4 to 3, which is the same as 1.334 to 1. That means the empirical formula is Fe3O4. Does that bother you? Think for a moment. This suggests it's an ionic compound. You know the charge on the oxide ion. You expect that to be 2-. So then the charge on each iron ion in this formula has to be positive 8/3? That doesn't sound right. There's something weird going on here. So either you completely screwed up the mathematics on this problem, or there's something else. Well, there's something else. Here, let's take a look at the 2 common oxides of iron. There's iron 2 oxide, and this is a pure sample of it. In the mineral form, it's found as wustite. And here On the right side is iron 3 oxide, and its mineral form is found as hematite. Now, neither of those, FeO or Fe2O3, match our empirical formula of Fe3O4. That's because this is something called magnetite, which is also known as lodestone. It has a combination of iron 2 and iron 3 oxide in it. And what obscured that was you were only told the masses of the elements, not the charges. So in a mole ratio, the iron 2 and iron 3 oxides are combined together in a mole ratio of 4 moles of oxygen to 3 moles of iron. So mole ratios to watch out for that you just can't round off and be done. Multiples of a tenth, a quarter, and a third. Any of those, you need to take one extra mathematical step to determine the proper empirical formula with small whole numbers.